Hello again. So still we are going through basic signal processing concepts part 2. Today we are going to discuss some basic terms: frequency, spectrum and bandwidth. So electromagnetic signal is one of the medium used to transmit data. A signal is generated by the transmitter and transmitted over a medium. The signal is a function of time, as we have seen in our previous section, like f of t. Signal is a function of time, but it can also be expressed as a function of frequency. So a signal can be viewed in two ways: in function of time and in function of frequency. That is, the signal consists of components of different frequencies. So when we see the function in time, like we have this wave, this is the waves or signal with function of time. So we can see at any particular time we can have a value of the signal. Or t time at t2 we can find out the value of the signal, but we cannot see the frequency information at particular time. Like we cannot see that what would be the frequency at this time or at this time. So we need to convert that into frequency domain, where we will see the signal representation in frequency domain. For example, if this wave or signal is sum of 1, 2, 3, 4 frequencies, one is f1, other is f2, and the next is f3 and f4. So here we can see that if this is the signal f of t, then this will be f of f. We convert that into frequency domain. And do you remember how to convert that? Yes, by using Fourier transform, as we have learned in previous lecture. So in frequency domain you can see that what frequencies exist in this signal, but we are missing one thing here, that we cannot find time in frequency domain. So in one domain we miss frequency parameter, and in another domain like frequency domain we miss time parameter. So this is some sort of a similar problem faced by a German scientist, Heisenberg uncertainty principle. Let's move forward. It turns out that the frequency domain view of a signal is more important to an understanding the data transmission than a time domain. So it says that frequency domain is more valuable, or it contains more information. Time domain concept views as a function of time. An electromagnetic signal can be either analog or digital. Analog signal is one in which the signal intensity varies in smooth fashion over time. So you can see this is analog signal, where you can see signal varies in smoothly there is no abrupt change, while in digital signal intensity maintains a constant level like this for some period of time and then abruptly changes to another level. There is no third level. Sorry, it's my mistake. So there is no. The continuous signal might represent speech and the discrete signal might represent binary 1 and 0. The simplest sort of signal is a periodic signal in which the same signal pattern repeats over time, otherwise a signal is aperiodic. The sine wave is the fundamental periodic signal. A general sine wave can be represented by 3 parameters. So any sine wave is represented by these 3 parameters: amplitude, frequency and phase. So you can see we have started from here. So if this is the time and if this is 1 second, that is called frequency, and this is amplitude. And the phase is that from where it started. It might start from here, or it might start from here. So this is called phase angle. The peak amplitude is the maximum value or strength of the signal over time. Typically the value is measured in volts. The frequency is the rate at which the signal repeats, and phase is the measure of the relative position in time within a single period of signal. More formally, for a periodic signal, f of t, phase is the fraction part of t of period, or the period t through which t has advanced relative to an
what is the
arbitrary
spectrum?
origin. Frequency, spectrum and bandwidth. The spectrum of a signal is the range of frequency that it contains. As I have shown that if we have a signal, we can convert them into frequency domain, like from where we can see how many sine waves constitute this signal. So f1 from f5, so we will see that we will say the range of the frequencies are from f1 to f5, and this is called spectrum. For the signal of figure A, the spectrum extends from 1f to 3f. So from the figure you can see there are 3 signals: 1f, 3f, and 2f is absent. So from 3f to 2f, so this is the spectrum, 1f to 3f. And from upper, if you subtract upper frequency, if you subtract lower frequency from upper frequency, in this case 3f minus 1f, you will get 2f. This is called bandwidth. Most of the energy in the signal is and we can see there are 2 type of frequency domains. In one we can see there are some limited number of sine waves, but here there is unlimited sine waves, relatively unlimited. So this contains infinite bandwidth. However, most of the energy in the signal is contained in a relatively narrow band of frequencies. This band is referred to as effective bandwidth or just bandwidth. So we are not going to use the infinite bandwidth. We will use some narrow band where we will leave those frequencies that has less energy, we will leave them and we will pick only those frequencies that has some significant energy. And what is spread spectrum? Okay, that's an interesting topic. The need for spread spectrum realized in World War. Before, they were using some specific frequency for data transmission. For example, this guy and this one is communicating with one another on a signal 13 megahertz. Okay, 13 megahertz. If this is the transmitter, this person transmitting and this one need to receive those signal. So for this person B to receive the signal, it has to tune its receiver at 13 megahertz. So as it set its radio at 13 megahertz, it will start receiving that the signal from person A, or participant A. If someone knows that frequency 13 megahertz, like a person C, and it knows that at which frequency these two guys are communicating, and if it set its own radio at 13 megahertz, it can easily pick those signals and sort of start listening. That problem faced in World War, and then an idea came that we don't need to send a signal on a single frequency, rather than we should transmit the data into spread spectrum. And how they do that, we are going to see in the coming topic. So spread spectrum is an important form of encoding for wireless communication. The spread spectrum techniques was developed initially for military intelligence requirements. The essential idea is to spread the information signal over a wider bandwidth to make jamming and interception more difficult. Input is fed into a channel encoder. So there will be an encoder. Input will be sent, like for example 1. The encoder has some random sequence. It will add, you can say it will add some more bits inside. You can say decode it. For 1, let's suppose we have 110. So rather than using for example this one will be sent not only 13 megahertz single frequency, but the range of frequencies, for example from 5 megahertz to 20 megahertz. So some of the information will be sent on 5 megahertz, some will be sent on 7 megahertz, some will be sent on 10 megahertz, some will be 20, and similarly so on. Some will be sent on 20 megahertz. Now input is fed into a channel encoder that produces an analog signal with a relatively narrow bandwidth around some center frequency. This signal is further modulated using a sequence of digits known as spreading code or spreading sequence. Typically, the spreading code is generated by a pseudo noise or pseudo number generator. We have gone through with the pseudo noise. And what is the encoder? In World War, I don't know was it first or second, but the frequency hopping spread spectrum was designed by and mathematician Hedy Lamarr.